In this video, we are going to discuss about JK flip-flop. So JK flip-flop, the JK means Jack Kilby, which is one of the famous electrical engineer. Now, JK flip-flop, it is very similar to the SR flip-flop. In addition, the indeterminate condition that present in SR flip-flop is permitted in JK flip-flop. That is 1-1. Input 1-1 is an invalid condition for the SR flip-flop, but that is permitted in JK flip-flop. So first we can go through the truth table. So slide shows the truth table. Here, when the clock signal is 0, we know that whatever be the value of inputs, your output will not change. Now, when the clock signal is 1, your output will change according to the input combination. So when j is equal to 0 and k is equal to 0, the output will be same as the previous output. That means state will not change. Now when j is equal to 0 and k is equal to 1, your output is 0. That means your flip-flop get reset. And when j is equal to 1 and k is equal to 0, the output get set. Now when j and k both are equal to 1, so this is the condition that is not allowed in SR flip-flop. So in JK flip-flop, when both inputs are 1, the condition will be a toggle condition. That means whatever be the previous output, its complement will be the current state. If suppose the previous state is 1, the current state will be 0. Or if previous state is 0, the current state will be 1. That means you will get a complementary output. Next is the logic diagram for the JK flip-flop. So the slide it is given for JK flip-flop. You can see that there are 4 NAND gate is used, and J, K and clock signal are the inputs. Q and Q bar are the outputs of JK flip-flop. Now this is a simple use represent the JK flip-flop. These are the J inputs. This is the K input. So Q and Q bar, and in addition there is a clock signal. Now you can see there are 2 other pins, PR and CLR, that we will discuss later. This PR, it is nothing but a preset, and this CLR, it is clear. So these 2 pins we will discuss later. Now we can just go through the working of JK flip-flop. Next we can discuss the operation of JK flip-flop. We can take the input combinations one by one. So first we can take j is equal to 0 and k is equal to 0. Now when j is equal to 0 and k is equal to 0, in that we have to apply the clock signal, then only your flip-flop will work. So this signal should be equal to 1. Now this input, that is the third input of NAND gate 1, will be Q bar. This is Q bar, and third input of your NAND gate 2 is Q. So if you take NAND gate 1, the inputs are 0, 1 and Q bar. So its complement will be the output. So there is a 0, that means a 0 dot 1 dot a Q bar. Whatever be the value of Q bar, it will be 0. So 0 complement, it is equal to 1. Similarly, if you take the NAND gate 2, the inputs are 0 dot 1 dot Q. So that is again equal to 1. 0 dot 1, it is 0, 0 dot Q, that is equal to 0. 0 complement, it is equal to 1. So the output of NAND gate 1 is 1, and output of NAND gate 2 is also 1. Now if you take the NAND gate 3, the input is 1 and this is Q bar. So one input is 1, the second input is Q bar. So this is given to the NAND gate. So the output 1 dot Q bar, it is Q bar and its complement will be equal to Q. So the output of NAND gate 3 will be Q. Now this Q is getting fed back as the input of NAND gate 4. So if you take the NAND gate 4, one input is 1, the second input is Q. So its complement, that means 1 dot Q is Q. So at the output you will get Q bar. That means your current state, that is after applying the state, your input, the state will remains as Q and Q bar. There will not be any change for the state. Next input combination is 0, 1. That is J is equal to 0 and K is equal to 1. So you can take J is equal to 0 and K is equal to 1. So clock signal you have to apply as 1. This is Q bar and this is Q. So if you take the NAND gate 1, the inputs are 1, 0 and Q bar. So the output will be 1. Now if you take the NAND gate 2, the inputs are 1, 1 and Q. So if you take its complement, this will be Q bar. 1 dot 1 is 1, then 1 dot Q is Q, its complement, that is Q bar. So the output of NAND gate 1 is 1, the output of NAND gate 2 is Q bar. Now if you take NAND gate 3, first input is 1, the second input is Q bar. This is Q bar. So NAND gate 3, if you take, first input is 1, the second input is Q bar. So its complement, 1 dot Q bar, it is Q bar, its complement, it is Q. So the output of NAND gate 3 will be Q. Now this Q is getting fed back as the input of NAND gate 4. So if you take NAND gate 4, the first input is Q, the second input is Q bar. So its complement, Q dot Q bar, it is nothing but 0 and its complement, so Q dot Q bar, it is 0 and its complement, it is equal to 1. So Q bar will be equal to 1. Now when Q bar is equal to 1, we know that the NAND gate 3 output is Q. So Q bar, it is 1. So the NAND gate output 3 is Q, that is equal to 0. So when J is equal to 0 and K is equal to 1, Q will be equal to 0 and Q bar will be equal to 1. So your flip-flop is said to be reset. Now the next state is J is equal to 1 and K is equal to 0. Now when J is equal to 1, K is equal to 0, this is Q bar and this is Q. So if you take NAND gate 1, the inputs are 1, 1 and Q bar. So if you apply that to a NAND gate, you will get Q as the output. Now if you take the NAND gate 2, the inputs are 1, 0 and Q. If you take its complement, it will be always 1. So the NAND gate 1 output is Q, NAND gate 2 output is 1. If you take NAND gate 3, one input is Q and the second input is Q bar. So if you take NAND gate 3, first input is Q and the second input is Q bar. So if you give that as the input of a NAND gate, that will be Q dot Q bar, it is 0, its complement, it is equal to 1. That means Q will get equal to 1 So this is getting fed back as the input of NAND gate 4. So if you take NAND gate 4, the first input is 1 and the second input is also 1. Its complement is equal to 0. So you will get Q as 1 and Q bar as 0 when you apply J is equal to 1 and K is equal to 0. So your flip-flop is said to be set. Next state is J is equal to 1 and K is equal to 1. So this is equal to 1, K is equal to 1, clock should be 1. This is Q bar and this is Q. So if you take NAND gate 1, the inputs are 1, 1 and Q complement. So the output of NAND gate 1 will be Q. So this will be Q. Similarly, if you take NAND gate 2, the inputs are 1, 1 and Q. So the output will be Q complement. So this will be Q complement. Now if you take NAND gate 3, one input of NAND gate 3 is the output of NAND gate 1. The second input is the output of NAND gate 4. Currently the output of NAND gate 4 is Q complement. So Q complement. So the input of NAND gate 3 are Q dot Q complement. So the output will be Q dot Q complement. It is 0. So its complement it is equal to 1. So you will get this as 1. Now this 1, that is the output of NAND gate 3, is getting fed back as the input of NAND gate 4. So if you take NAND gate 4, first input is 1, the second input is Q complement. So if you take its complement, the output will be Q. That means the current output, that is current output of your flip-flop 4 is Q. So this is Q. Now this Q is getting fed back to the input of your NAND gate 3. So now the NAND gate 3 input become Q and Q. So one input is Q, the second input is again Q, its complement, that is equal to Q complement. That means this will become Q complement. Now this Q complement is getting fed back as the input of NAND gate 4. So this is Q complement. Now the second input is also Q complement. Now if you take the NAND gate 4, you'll get both input are Q complement. So its complement, that is equal to Q. So now it become Q. So now it is a stable condition. Q is getting again fed back to the input of NAND gate 3. So Q and Q. So the output will be Q complement. So that is the stable state. That means if you are giving J is equal to 1 and K is equal to 1, you will get the output as the complement of the previous output. That means if Qn is equal to 0, Qn plus 1, next state will be equal to 1. If Qn is 1, the next state will be 0. So that is why this state is named as toggle condition. So that these are the 4 states for input combinations that is possible for the JK. So in the slide, the timing diagram of JK flip-flop is shown. There is a different combination of J and K, and this is the clock signal, this is the output Q. So when your clock signal is becoming high, or when you apply a high signal at the clock input, it will check the input combinations, and according to that your output will change. Now when the clock signal is 0, whatever be the combination of the input, the output will not change. So the first high signal for the clock signal is coming at this instant. At that time, j is equal to 0 and k is equal to 1. When j is equal to 0 and k is equal to 1, your output will get reset. That means it will become 0. Now in the next clock signal, that is here, you can see that your j is equal to 1 and k is equal to 1 here. So when j is equal to 1 and k is equal to 1, we know that it is a toggle condition. So previously your output was 0, so that get toggled and it will become 1 during this interval. Now here, even here this condition, your clock signal is present, but your input is 0 0 at this instant. So 0 0 means there is no change, so output will remain as the previous state. So similarly, you can see the different instant of the clock signal and the corresponding input and output combinations in the timing diagram.